Okay, so we're going to get started on section 2.3. And in this section, we're going to be talking about the greatest common divisor of two integers, as well as we're going to generalize this to a finite number of integers, the greatest common divisor of n integers. So let me start with a definition. It says you that with a and b be integers and integer b does not equal to 0 is called or is said to be a common divisor of a and b if, as you would expect, b is going to divide both a and b divides b. We are interested in looking at all common divisors of two integers. First, let's start with this. If a is equal, b is equal to 0, then every b does not equal to 0, where b is an integer, is a common divisor of of a and b. And this is true since if b is not equal to 0, since d divides 0 and d divides 0, right? That's ridiculous to write yes, but it's actually for both of these. Because we can always write 0 as a multiple of d by using 0. So in other words, this implies that the set of all divisors or common divisors of 0 and 0 is infinite. And hence it does not have a greatest common divisor. In other words, the concept of the greatest common divisor means it's meaningless. This means and the greatest common divisor, by the way, we denote by this. I'm sure you're familiar with this. Even the CD, we're going to remove that. And then we put 0, 0 has no meaning. Okay, so we're not going to assign a value for this. However, if at least one of A or B does not equal to 0, means they are not both equal to 0, then we're going to see that the set of common divisor is finite. And in particular, we are interested is actually in the positive divisors, positive common divisors between A and B. All right, so let's make this a statement. And again, here we are taking the intuitive meaning of a greatest common divisor to be a common divisor that is not largest among all of these. Okay, that's the way we're going to define this. All right. However, if not both A and B equal to 0, then the set of positive, that's what I say we want to be interested in, positive divisors is non-empty and finite. Now we're going to prove this, okay? Really, this is very simple, okay? So this is not proof. So we're going to assume that not both A and B equal to 0. And with all loss of generality, let's assume that A does not equal to 0. All right? We're going to define this set. We're going to define S to be those x in natural numbers such that x is a common divisor of A and B. Remember that even if one of these is 0, then x a natural number would divide 0, all right? Actually, every non-zero number actually divides. All right, so these are positive. By the way, we are taking x to be actually a natural number, all right? First, we're going to show that S is not empty, all right? Now, we know that 1 divides A and 1 divides B. This implies 1 is actually in S. So this means S is not empty. All right. The next thing I want to show that the number of these common divisors, okay, positive common divisor is finite. In fact, we're going to show that this set is bounded above, basically. All right? And to do this, so let's assume that x is a common divisor, means it belongs to this set. Okay, so let x belongs to S. So this implies that x divides A and x divides B. Now, if x divides A, then x also divides the absolute value of A, all right? And x divides the absolute value of B. Also, we have shown that if x divides a number, then this implies that x is less than or equal to that, all right? Because absolute value is going to be a multiple of x, so it's going to be x is going to be less than or equal to this, as well as, and x is less than or equal, sorry, not divide, less than or equal. All right? Now, and with this, then actually let me do something before this, okay? from both of these, we have shown that X would divide any linear combination of the absolute value of A, absolute value of B, and this is what I need. We need that this divides this. And this implies that X is going to be less than or equal absolute value of A, absolute value. All right, so any divisor means, any element in S is going to be smaller than or equal the sum of the absolute value. So this implies S is bounded, what we call, above. All right, and since this is a set of integers, this actually positive integer, since S is a subset of natural numbers, it has and bounded above, okay? So it and bounded above, let me write this down. Bounded above. This implies that S has a maximum, has a greatest. L. Let's say D. All right? This D we define to be the greatest common divisor of A and B. So what we have shown in here is really if not both A and B are equal to 0, then there exists this greatest element that is a common divisor of both of these, because this D is actually in S. All right? Well, let's actually formalize this. Right? This is as a definition. And what we have already here, we established that the definition actually makes sense. It's the existence, basically, of greatest common divisor is guaranteed. All right? So here it is. Definition. Let A and B be integers, positive, negative, whatever, not both of which, not both equal to 0. A positive integer D is called the greatest common divisor of A and B. Okay, so this is the concept that we are defining. Divisor of A and B, denoted by greatest common divisor of A, B equal D. Or we simply write, we denote it by AD. And that's not going to be confusing this with an ordered pair or an interval, because it's going to be clear from the context that we're talking about this. Is equal to D. All right? common divisor, this notation by this, if, as you see, we're already saying it's a positive, okay? So if D, actually two conditions that we put here. If D divides A and D divides B, means a common divisor. Two, if C divides A and C divides B, means C is a common divisor of both of these, then D is bigger than or equal to C. So it is the largest among all common divisors of A and B. We're going to look at other characterization of this. We're going to actually prove that D can be described in a different way than this. So this is, at least it reflects the meaning of the greatest common divisor. All right. Now, in this definition, in order, if we want to apply it, okay, as is, in order to find the greatest common divisor of two integers, means we need to find basically all the positive divisors of the two integers and take the actually the largest among these, this set. All right, means the intersection basically of the common divisors, and we're going to take the largest, all right, among these common divisors. This is okay for smaller values of A and B. However, when A and B are very large, this is actually, it's almost impossible to apply. And when we're talking about large, okay, integer means integers that have 100 to 100 digits, okay? And even with the use of computer, this is not something easy to do, all right? Later on in this chapter, we're going to be talking about a more efficient method of evaluating, computing, calculating the greatest common divisor of two integers by what is called Euclidean algorithm, which is basically applying the division algorithm repeatedly. Okay, so this is something that we're going to be talking about. So I'm not going to be concerned very much of finding the greatest common divisors. Just a simple example. If you want to look at the greatest common divisor of, for example, 18 to 24, you're going to find this is equal actually to 6. Okay, so 6 divides 18 divides 24, and among the divisors of 18, there is a 9, which is bigger than this, but 9 doesn't divide this, and so on. So you will find this is it. All right? All right. Even when we talk about greatest common divisor of negatives and 2, we always take the greatest common divisor to be positive. So this is going to be equal in this case to 2. Okay? And even if this is negative, still we have this is equal to 2. All right. Let's start with actually one other thing. You will notice that for any b does not equal to 0, greatest common divisor of 0 and b is equal to b. Because from here, of course, b divides 0, okay? And b divides itself, and the largest positive, among the divisors of these, all right, is going to be equal to b. We need both of them, all right? We know that 0 has infinitely many divisors, okay, all the integers other than 0 itself, but we need a common one, and that's leads us with b. Here is the first characterization of greatest common divisor, and this is theorem 2.3. All right. 2.3. So this is characterization of greatest common divisor of two integers. So characterization of a certain property, all right, or a certain concept means this serves as actually a definition for the concept. It gives the necessary sort of a sufficient condition for the greatest common divisor, other than the definition that we took. All right, so let's start with this. Again, let A and B be integers, not both equal 0. Actually, whenever we talk about the greatest common divisor and we don't make this statement not both equal to 0, it's implicitly, it should imply that, should be included, all right? And we can then let the greatest common divisor AB is equal to G. Okay, so I'm assuming writing this is without the GCD rather. All right. Then G is the least positive integer of the of all, okay, positive integer of the set of all. Wait, so the least positive integer of the set of all positive integers of this form. Ax plus by such that x, y actually ranges all over the integer c. All right. This means that is G is equal Ax sub 0 plus By sub 0 for some integers x sub 0 and y sub 0. Let me put first of all here a warning. Expressing G in this form is not unique. So this representation of G is not unique. For example, it's not very hard to see. You could write G as A and x sub 0 plus B y sub 0 minus f. And you call the x sub 0 plus B, you call this is x1, and you call this is y1. All right? And when you multiply through, you're going to see that the AB and the BA minus BA, they cancel out, so it gives you the same as G. So this representation is not unique, but means we always can find at least two integers, x sub 0, y sub 0, to write G as in this form. All right? All right. we're going to go ahead and prove this. And again, we're going to be using the will ordering principle. All right? We did before. So I want to define a set of the integers that are combinations of A and B. And then we're going to take the subset that consists of the positive ones. All right? So, okay, here's the proof. We're going to define C to consist of AX plus BY, such that X, Y are integers. And we're going to let C plus be the subset of C whose elements are positive. So we may say actually non-negative. Non-negative. We could allow even 0 there. It's not going to be any problem. Okay. But I claim first that C plus is not empty. All right. Now remember that since A and B are not both equal to 0, let's assume, without loss of generality, that A does not equal to 0. This implies that, and then I want to come up with actually an element in C plus. Then if A is bigger than 0, then this element A, which is equal A multiplied by 1 plus B multiplied by 0, belongs to C plus. All right? If A is less than 0, then minus A, which is equal A multiplied by negative 1 plus B times 0 is also in C plus. So we would take the multiple to be negative 1 in this case. But, so therefore we do have an unempty set. Now, by the will ordering principle, C plus has a least element. Let us call it L. Okay? We're going to call this is L. All right? Now, I'm going to, what does this mean? This means L is equal to, wait, write this down. So this implies there exists an X sub 0, Y sub 0 in Z such that L is equal AX sub 0 plus BY sub 0. All right? And we know by choice that this is bigger than 0, all right? We know this is, we're taking the elements to be actually bigger. Well, I said non-negative, so I guess we proved that it contains a positive. So we could actually make the C class to consist of all positive, okay, elements of this form, basically. Of course, the x and the y without the x sub 0. What I'm going to show that actually G is equal to F. So I have a claim that G is equal to F. All right? And the way we're going to do this is let's see that L is a common divisor of both A and B. All right? And in other words, we're going to show that G is less than or equal to L and L is less than or equal to G. So with both of these, it's going to give us they are equal to each other. All right? Now, first let's look at to show L divides A. Okay? So I'm going to do this by contradiction. So let's assume that it doesn't. Assume that L does not divide A. And yes, it's going to lead to a contradiction. All right? So L does not divide A. Now, we know that we're going to apply the division algorithm to L and A, and this allows us to write A as LQ plus R for some integers Q and R, where the remainder R is actually bigger than 0 and less than L. The reason we cannot have R equal to 0, because if R equal to 0, then actually L will divide A. Okay, so here R does not equal to 0 since L does not divide A. Because if it does, then we have R equal to 0. All right, so we have this. All right, now let's look at what R is equal to from this equation. So R is equal A minus LQ. And let me write what L is equal to. This is L. So we're going to replace this for L in here. So this is A x sub 0 plus B y sub 0 Q. And we can rewrite this and arrange it as A times 1 minus x sub 0 Q plus or minus A, well, let me put a plus in here, B times minus y sub 0 Q. All right, so we come up with an element. This is actually in C plus because it has the same form as elements in C, as well as because R is positive. All right, so this is positive, so this belongs to C plus. Well, we have a contradiction in here because we are saying that the R is smaller than L, but we have the L is the smallest element in C plus. Okay, write this down. Since So we have, let me actually say it this way, so we have, or we have shown that R is in C plus, and since R is less than L, this contradict that L is the least element in C plus. All right? Okay, so this means that we must have, so therefore, L must divide A. Similarly, you know, I can show that L divides B by contradiction, by what I did. Similarly, L divides B. So this makes L is a common divisor. So this implies L is a common divisor of A and B. And by definition of the greatest common divisor, which we call it G, this implies that L is smaller than or equal to G. Okay? Since G is the greatest common divisor. Now I want to go conversely. All right? So I'm going to assume that, or show that L is bigger than or equal to G. All right, on the other hand, G being the greatest common divisor, A and B, by the definition, implies that G divides A and G divides B and something else, which is the largest. But this implies that G divides any linear combination. So it divides AX sub 0 plus BY sub 0. But this is equal L. So G divides L implies that L is bigger than or equal to G. All right, both of these are positive, remember, and then we have shown that if G is a divisor, okay, of L, so which means that L is bigger than or equal any of its divisors, basically, very simple. So both of these implies that we have G is equal L, and which is this integer of this form. All right? Let's look at some corollaries of this. Here's the first corollary. Again, we are going to assume that A and B are the integers, not both equal to 0. Then we're gonna let P consist of this set. let me call this a C, that like we did before, okay? All right? Then, this set C is the set of all multiples, so then C is equal to this set, KD, such that K is an entity. All right? So the set of all linear combination of A and B is the same as the set of multiples of the greatest common, and maybe I need to write this down. Okay, so the P and K, and you're going to let D equal the greatest common divisor of A and B. All right? Then, okay, we're going to let this, and we have that. All right, here's the proof. Actually, there are two sets in here. The C, and in the other set, let me call it actually this set capital D. All right? So we're going to let capital D, or capital K, maybe, better. But we call it capital K. So this is the multiples of these such that K is in C. Our objective is to show that each one of these sets is contained in the other. All right? So let's start by the following. Okay, so we have D divides A and D divides B. Implies that D, all right, divides any combination. All right, which means by definition that AX plus BY is equal DK for some K in Z. This means any element in here, because any element in here, so this implies for every T in, we call it little c here. This implies for every little c in C, C is equal to D. All right? So this proves that actually C is contained in K. All right? So any element in C is going to have this form AX plus Y. Or so that therefore we have C is contained in K. Conversely, okay? We're going to take an element from here and show actually it can be expressed as AX plus BY, all right? So I know that, again, D by the theorem, like theorem 2.3, the theorem we proved, we know D is equal AX sub 0 plus BY sub 0 for some X sub 0, Y sub 0 is in Z. All right? Now let me multiply this is by K. So we're going to multiply this is by K. So this implies that KD is equal A KX sub 0 plus B KY sub 0. And we can write this as AX prime plus BY prime. definitely belongs to C. All right? And this is an element, an arbitrary element actually from KD, so this implies that K, the set K is contained in the set C. So both of these implies they are the same. All right? So this might look at kind of a strange result, but actually this is important in ring theory. All right? So it has some significance in other places in mathematics. All right. We move on to reducing some other concepts. Now, let me put actually here a remark. So theorem 2.3 implies that the greatest common divisor, we call it D, can be expressed as a combination. All right. So in other words, if this is equal to D, then D is equal AX sub 0 plus BY sub 0 for some X sub 0, Y sub 0 in D. The converse of this statement is not true. Converse of this statement is not the truth. Okay, what does this mean? That is, if we have a linear combination, let me call a different letter in here. If G is equal AX sub 0, BY sub 0 for some X sub 0, Y sub 0 being integer, then it is not necessarily true that G is equal the greatest common divisor of A and B. All right? All right, now we stop for a minute here. I wanted to go get some water. Okay, so let me give you an argument why this converse is not true. So let's assume that we have actually G, all right, is of this form. So assume that G is equal A X sub 0 plus B Y sub 0. If I multiply both of sides of this equation by K, where K is a positive integer, okay, so we're going to multiply by K positive. This would imply that GK is equal A K X sub 0 plus B K Y sub 0. Well, it has the same form, then this would imply that the greatest common divisor of AB is going to also equal GK for every K being positive. Well, that's else can be this true because the greatest common divisor is unique. So this is not possible. Alright, so in general, this is not true. However, if the greatest common divisor is equal to 1, or 1 is written in this way, then it turns out that 1 is going to be the greatest common divisor. I mean, the converse is true in the case where the linear combination of A and B is equal to 1. So I want to state this as a theorem. Sometimes we refer to this theorem as Bazut Lemma. Yeah, this is literally called. And here it is. All right, so this is theorem 2.4 in the book. And it says that, again, that A, B, be integers, not both 0. Then the greatest common divisor of A, B equal 1 if and only if one can be written as AX plus BY or sum X, Y, and Z. So it is an if and only if. Okay, so let's go with the proof. Let's go this way. If the greatest common divisor of this is equal to 1, then by theorem 2.3, 1 is expressed this way. Then 1, there exists X, Y, in Z such that 1 is equal to AX plus BY. Or you could call them X sub 0, Y sub 0 if you wish, but this way is fine. Now you need to go the other way around. So this time we're going to assume that there exists X, Y, in Z such that 1 is equal to AX plus BY. And you need to show greatest common divisor of this is equal to 1. Well, let's assume it is equal to B, all right? And we'll see what the D must equal to. So let's assume that greatest common divisor AB is equal to D. Then this would imply that B divides A and D divides B. And this again would imply that D divides the linear combination of these. And I want to take the linear combination to be this X and this Y. Okay, so there's. But this is equal to 1. So this implies D divides 1. And this in itself implies that D is less than or equal to 1. But by definition, D must be positive, okay? So it must be bigger than or equal to 1. And that will take care of the proof, all right? Okay, but D bigger than or equal to 1, since D is a natural number. So therefore, D must equal. Okay, so the converse in this case is true. Now, we use a special term for the case when two integers, the greatest common divisor is equal to 1. We call such integers relatively prime or co-prime. So I'm going to put this definition, which we're going to see it quite often. Okay. Here's the definition. Two integers are said to be relatively prime or co-prime if the greatest common divisor AB is equal to 1. All right? Well, actually, we can generalize this a little bit more. So more general statement, a set of integers a1, a2, up to an, not all of which equals 0, is said to be pairwise relatively prime or co-prime, pairwise co-prime if the greatest common divisor of AI, AJ is equal to 1 for every AI does not equal, for every I does not equal to J, basically, right? For every I does not equal to J, and these runs, of course, between 1 and n. Or sometimes we call these are relatively prime in pairs. All right? Well, the next thing we would like to look at is some properties, all right, actually, of the greatest common divisor. There is a theorem. Okay, the theorem. For any positive integer m, and the usual A and B are integers not both equal 0, the greatest common divisor of MA, MP is equal M times AP. So you can take a top, all right? It's not very hard to believe this, of course, is true, all right? But here is a proof, okay? By definition, or by theorem, not by definition, by theorem 2-3, we have the MAMB is actually equal to the least positive value of this, AX plus BY, as X and Y ranges over the, actually the integers, okay? Where X, Y ranges over the integers. All right, no, sorry, M, I need a seed value of, we have more space here, value of MA times X plus MB minus Y, where X and Y again ranges over there. Now we can take a common factor between these, so you could say this is the, again, least positive value of M times AX plus BY. Now, since M is a positive integer, we actually can remove it outside in here. It's not going to affect. Then we're going to look at the least positive value of AX plus BY. So we're taking positive value here. And this is equal M times A. All right. The next theorem that we're going to prove actually it's uses this, and it's a slight modification of this theorem, and it goes like this. Again, A, B, and C, not both 0. D divides A, and D divides B, with D being a positive. Now, I'm not saying D is the greatest common divisor, okay, of A and B. It's just a common divisor. It's a positive common divisor. Okay, so D is a positive common divisor of A and B. Not necessarily the greatest common divisor. Then we have the greatest common divisor of A over D, B over D is equal 1 over D, A, B. All right? We cannot say that the M is equal 1 over D in here, all right? Because that will be not an integer, okay? So kind of it doesn't apply. So another thing, so this is 1. If actually D is equal to the greatest common divisor of A and B, then A over D, the greatest common divisor of A over D, B over D is equal to 1. All right? So we come up with a special case. All right. Let's go ahead and prove this. Simply, we can apply the previous theorem. Okay, let me actually put the proof in here because it's so simple. we're going to apply the previous theorem. With M equal D. And we're going to look at one other thing in here. This A over D does make sense. I mean, this is an integer because D divides A and D divides B. So we are fine in here. In here it looks like funny because, you know, we have 1 over D. And as far as this whole thing is an integer, then we are saying that that integer is equal to this. Okay. All right. So in actuality, it is because, you know, whatever the greatest common divisor for A and B, and this is just a common divisor, so it actually divides that. So D is a divisor because that's going to be the largest. All right. So here what I'm going to do, I'm going to look at D multiplied by A over D. D multiplied by B over D. So I'm applying again this M, and this is my integer here, another integer. So according to the previous theorem, we can take the D out, and then we have left in here the A over D, over D, and then B over D. But we have D times A over D, this is equal to A, and this is equal to B, and this is D times that. And then I can divide both sides by D. All right, so dividing by D, we come up with 1 over D. AB is equal greatest common divisor A over D, B over D. All right. Now the second part, so this is the first part. For the second part is again, we apply the first part. Okay? Now, since we had, since D is equal greatest common divisor of AB, actually take this one out, we don't need this anymore here. All right, so D is equal to this, and this implies if I divide by D, we get 1 over D. But this one is equal to, just we showed in here, is A over D, B over D. So this equality by 1. Okay. All right, let's move on to look at some other properties. Actually, this is a property for both the divide together with the greatest common divisor. So let's go. In fact, this is a corollary that follows from what we is talking about in here, corollary. It reads like this. If A divides C, and remember in here we are assuming that A does not equal to 0, and B divides C, and the greatest common divisor, A and B, is equal to 1, then AB divides C. All right? All right. So let's look at the proof here. So A divides C implies I can write C as AR for some R in Z. Similarly, B divides C implies I can write C as AS for some S in Z. All right? We have now one other thing, the AB equal to 1. In fact, almost as a rule, whenever you are given the greatest common divisor of two integers to equal to 1, you're going to be using this absolute lemma, which says that then this implies there exists x, y in Z such that 1 is equal a x plus b1. Now we're going to substitute we're going to multiply this first by c. Okay, so we're going to multiply this by c. Okay, so this would imply that c is equal acx plus bc1. All right. Now, no, actually, this is BS. All right. Now let's substitute for the C in terms of. So also we could write this one as AR x plus BS. Surely I don't think I need this. Okay, let me see. Actually, yes, that's right. All right, BSY. And let me factor out an I'm sorry, this is the wrong substitution here. Okay, so for the first C, I'm going to write this one in terms of B. I'm sorry. So this is equal ABS x plus B, and I want to substitute for the C by AR. Now then we have an AB as a common factor, so this is AB. Then we can write this one as SX plus RY. And this is exactly what it means. We are expressing C as a multiple of AB. So from here, we conclude that C divides AB. All right? Because C is actually a multiple of, AB divides C. AB divides, okay? Not the other way around. All right. Please look next what I want to do. Here is a very important, actually, lemma. It's called Euclid's lemma. And this is given as theorem 2.5. Okay. The clean board. And 2.5. And we revert to this as Euclid's lemma. Okay. Again, another useful result that we're going to see over and over again is that if A divides BC and greatest common divisor A and B is equal 1, means they are relatively prime, that's another way of saying this, then A must divide C. Actually, either, right, yeah, that's all I need. Right. Here's the proof. Again, we're going to use that idea, the greatest common divisor of A and B is equal to 1. Okay. Implies there exists x, y, and z such that 1 is equal to ax plus b1. Again, let's multiply this is by c. So we get c is equal AC x plus BC y. All right. Now I know that A divides, so we have A divides BC, all right, and A divides AC, all right. So it divides actually this and this. Then this implies it divides any combination. So this implies A divides any combination called linear of BC and AC. So in this case, we're going to take the linear combination, of course, to be the ACX plus BCY. But this combination is equal to C. All right? And that's what we have. This is equal to C, so this implies A divides C. And again, this is very kind of intuitively, it's true. There is no common factor between A and B, and A divides this product. That has nothing to do, no common factor B, so the common factor must be with the C, okay, that divides. All right, let me move on with other consequences of this, actually of this theorem. Let's assume that there's a corollary. If B is a prime and P divides a product of two integers A, B, then either P divides A, P divides A, or P divides B, or both, of course. All right? All right, here's the proof. A simple argument means if, let's say, P divides one of these, let's say A, then we are done. Regardless of P is going to divide P or not, means because we have an O here. All right, so let's assume, no, assume that P does not divide A. Then we must show P divides B. All right? Well, let's see here. When we say that this, P does not divide A, this implies that the greatest common divisor of A and P, this is going to actually equal to 1, because the only common divisors, the only divisor to start with for the prime P is 1 and itself. All right? And since P does not divide, then P cannot be a divisor of A. So, of course, 1 is a divisor of A, and then we must have this is equal to 1. Then, by the theorem, so we have actually, so by the theorem, that is Euclid Lemma, okay, 2.5. We have P divides AP, and the greatest common divisor of AP is equal 1, implies that P must divide actually B, right? The B here stands for the C on that here. All right. Another also with corollary that if we have everything is a prime, if P is a prime and also divides a product of two primes, P1, P2, where P1, P2 are primes, then P divides, see here, actually it's equal this time, then P must equal P1 or P must equal. Alright, the proof is very, very straightforward because it must divide one of them, and then because the only divisors of these primes is themselves or 1, and this result false. So I'm just gonna leave this out for you. All right. Let me see in here. One other property, and then I want to give another characterization of a greatest common divisor. We use this one here. All right. Well, here's this important property, and it reads like this. Thus, we're going to use it in developing the Euclidean algorithm to calculate the greatest common divisor between two integers, and it goes like this. For any integer x, the greatest common divisor of A and B is the same as greatest common divisor of A, B plus AX, and this is also equal the other way around. A plus BX. All right? So in other words, what this is saying the greatest common divisor, and of course we could combine these together. All right. So it says that the greatest common divisor of AB, you could do the same as if you take a combination or replace the B by a combination of a term of a multiple value, or the other way around for the B. All right? So let's go ahead and prove this. So let's assume that we have two different. That the grade A and B is equal D, and the other side is equal G. And our objective is to show that D is equal to G. All right, now let's start with this one. So D equal AB implies that D divides A and D divides B. Also, from this one, we have D divides any combination of these. So, and in this case, I can take the combination to be AX plus 1 times B. All right, now we have, now D divides A and D divides the AX plus 1 B, sorry. All right, and this means that D is going to be a common divisor of these, and this implies that the G is going to be bigger than or equal to D, since G is the greatest common divisor of A and AX plus B. All right, so we have one inequality here. Now we need to do another inequality the other way around. And this time we start with G. G divides A, and actually here we are using G is equal the A, B plus AX. All right, so G divides this and G divides B plus AX. And so we're going to take a combination of these. And all I want to get is G to divide B. So I want to take this one. The combination is going to be A. Actually, let's see in here. So I want to multiply this is by 1 and multiply this is by, or subtract AX from it. Okay, so we're going to take the combination that negative XA plus B plus AX. Okay, so the combination from A and this one by 1. And this together is going to give me B. So this time that G is a common divisor of A and B. And since D is the greatest common divisor of these, then D must be bigger than or equal to G. So these two inequalities together, this one and this one, would imply that D is equal to G. All right. Almost at the end, we need to give one more characterization. Actually, it's a nice one for greatest common divisor. Actually, this next characterization usually is given as the definition. In some textbook, some author use this as their definition of the greatest common divisor. All right, so here's another theorem. This is the last theorem in the book, is 2.6. And again, it's a characterization or another characterization of a greatest common divisor. And it reads like this, okay? Let me state it the way it is stated in the book. And let A, B be integers, again not both equal to 0. For a positive integer D is the greatest common divisor of AB if and only if these conditions are satisfied. One, D is a common divisor, divides A and D divides B. Second condition is if we have another common divisor, C divides A and C divides B, then C divides D. Now you can see from this, okay, actually what the proof in one way. Okay, so here it is. Now we're gonna take as the definition of a greatest common divisor what we gave before. Means it's a common divisor and it is the largest among all positive divisors. Okay? So let's assume that. So let's go this way. Assume that D is the greatest common divisor of A by the definition. Then we know that I want to show that it satisfies these two conditions. All right. Then D divides A and D divides B, because that's the way usually we took it. Then the next thing I want to show that let C divides A and C divides B, then I wanted to show that C actually divides D, all right? So I want to show that this one true. So, so in this case, we have, this is a common divisor for A and B. Then we know that actually C must be less than or equal to, all right, D. All right? Okay, I don't think this is gonna do it. But let me, all right, so what we have in here, let me actually use the following in here. We know that, let me use actually the theorem which states that, okay, so we have D actually is equal AX plus BY for some X, Y in C. All right. Now, divides A and C divides B implies C divides any linear combination of these, and I want to get this linear combination to be actually AX plus BY, which is equal to D. So in other words, condition 2 that B is satisfied. Is satisfied. All right, let's go the other way around. That is, let's assume that D is a positive integer and satisfy these two conditions. All right? And I want to show that it is the greatest common divisor. Okay, so let's go the other way. It's this way. So let's assume that D is positive and satisfy A and B. So what we need to show, that actually D is the largest, is the greatest common divisors, all right? From A, we have D is a common factor. Or a common, divisor, what I mean. Common divisor. Of A and B. The next thing we want is, it is the largest. So let's assume we C is another common divisor. From B, C is, if C is a common divisor, common divisor of A and B, then this is what the second condition say. Let's say C implies D. Well, this implies that the absolute value of C, because I don't know if it is positive or negative, is less than or equal to D. All right, we proved this. So if something divides, then absolute value is less. Well, D is a positive number, then we can write this as, absolute value inequality like this. So in particular, we do have C is less than D, and hence D is the greatest common divisor of A and B according to the definition, that it is the largest among all common divisors. And this will end the proof of this. Sometimes we need to look at greatest common divisor of more than one or more than two, basically, integers. The question is, can we generalize? And of course, yes, we can generalize the concept of greatest common divisor. And let me write the definition. Now we can choose, among all these different characterization. Okay, so let's assume that let A1, A2, up to AN, n bigger than or equal to 2, be integers, not all of which at least one is equal to 0. Equal to 0. Then the greatest common divisor of A1, A2, up to AN is the positive integer b that satisfy the following two conditions. One, D divides each one of these for every I between 1 and n. 2, if C divides AI, again for every I between 1 and n, then C divides D. All right, or you could define it as the common divisor of all AIs, and it is the largest, okay, positive common divisor. You know, the largest among all positive divisors of the AIs. And it's not very hard to also prove something like this. You take the greatest common divisor of all of these, A1, A2, up to AN. You can group these in any way you like. For example, you could say the greatest common divisor, we put inside, greatest common divisor, A1 up to AN minus 1 and AN. Okay? Now remember that, now also you could see this recursive relationship. All right? So the greatest common divisor of this from A1 to AN minus 1, that's going to be an integer, okay, a positive integer. And then you take the greatest common divisor of that with AN. And then you can, you know, actually go and do more of these. Greatest common divisor of A1 up to AN minus 2. And then take the greatest common divisor of AN minus 1 and AN. All kinds of combination actually does work there. All right, and also it is not hard to prove this, that is D is going to be a linear combination of all the AIs. Okay, so the greatest common divisor also satisfy or as this. Means D we could express as A1 x1 plus A2 x2 and so on. In fact, the greatest common divisor is the least, okay, positive value of expression like this, means among all possible combination of these, the least positive one is what D is equal. All right, I'm going to stop right here. And next time, we're going to start on the Euclidean algorithm that provides actually a very efficient method for calculating greatest common divisor when actually the integers are big, very big. And this algorithm is still in use. Okay.